what this means is, maybe I can draw it down. So in their paper, somewhere in the code, they had a kernel evaluation between vector 1 and vector 2, where they were doing some calculation, which means that for these 2 pixels, you need a feature vector, V1 and V2. You need feature vectors. And that is fine if you have RGB. However, if you have distances, for example, between these 2 pixels, depends on the distance between them, the geodesic distance between these 2. And so if I draw a scribble like this and make them equal, then the distance is set to 0. So if I give it the RGB vectors, the algorithm will get very confused because this may be red and this may be green. But just because I said those 2 are both foreground, I need to set an equivalence between the red and green pixel. And the way I can do this is I can explicitly write a distance matrix. So what I can do is I can take this image, and let's say this is a red circle and a green red circle and a green circle. And I take a pixel here, and just because I said that this and this are equivalent, right? What happens now is the red pixel vector and the green pixel vector need to be the same. But obviously RGB wise, they're not. So the way we do this is we write down a distance matrix where you have all the pixels in the image. So if you have, say, M cross, let's say 100 by 100 image, then you have 10,000 pixels. So you have 10,000 by 10,000 distance matrix. So the red pixel is here, green pixel is here. Okay. So the 2 distances that we are concerned with, it's a symmetric matrix, let's say, because it's a distance matrix like that. Let's say it's a symmetric matrix with where we are asking what is the distance. These 2 will be the same value. So we are saying that some distance at each element of this matrix, there's a distance between these 2. If you simply took the red vector and the green vector, you will get some distance, which is Euclidean, let's say. However, once you've indicated equivalence, what are we doing? We are setting the distances here to 0. Right? We are saying this pixel is equivalent to that pixel. So we are really warping this distance metric over the image. And instead of using L2 or whatever, we have a user-specified distance metric, which can be very ill-behaved because we set equivalences. You can think of it as you have this space where you have Euclidean points, which is RGB. And there's a point here and here. And imagine you took that whole space and warped it so that these 2 points are now the same vector. Then the rest of the space warps, right? And then you took some other 2 points and you warped those. So in the end, you end up with this space where the metric creates havoc. Like you don't really know what the vectors are. So then when you come back, you don't know what the vector is associated with these 2. Because every time you create an equivalence, you have to make sure you set these 2 to the same vector. And if you create so many equivalences by scribbling, then you really don't know how to come up with these vectors. Okay? And what does this mean? If you can't come up with the vectors, then we can't run their fast algorithm because their algorithm requires the vectors. And it cannot use any arbitrary distance here. It needs that Gaussian. If we replace that Gaussian with whatever distance matrix we had, then their whole method breaks down and we can't use it. So how can we do this? That's the problem that we started with and somehow ended up with this application. So when we started with the problem, we were just thinking of an interesting academic problem where somebody takes this space, chooses 2 points, and says these 2 points are equivalent, then chooses some other 2 points, says these 2 are equivalent, and then you keep warping it, and we were like, is this useful for something? And we went to the image space and said, oh, maybe we would want to say this pixel equals this pixel equals this, and so on. And it turns out that it's actually an interesting problem. It's not easy to solve. We have this arbitrary dissimilarity measure, distance metric, between pixels. You have 2 pixels, and you don't know what that is. Okay, and then somehow we need to go from here to there, and there are methods that have been known for many years which take a distance metric and give you an embedding. Okay. And today's lab is about programming such a thing, okay? And you'll see why it's useful. So maybe a slight detour on embedding before we see why sampling is useful there. Okay, so let's start with a simple idea. Okay, I tell you, so there is let's just take a 3 by 3 matrix. Again, this is Bangalore, Mysore, and Chennai. The distance between them is obviously all 0. Okay. Bangalore and Mysore is like 130, is it? 135? Depends on who you ask, kilometers. Bangalore and Chennai maybe 320. So Mysore and Chennai, I don't have any idea. Let's say 400. Yeah, that is if you take the roads. But we are going to assume you can fly. Okay, so let's say it's something like that. So actually, these numbers should be lower maybe. Anyway, so you have some distances like that, and Vijay probably knows this much better than I do. So correct me if I say anything that's wrong. 140 if you take the road. So we are assuming you can fly. Okay, so 320, 400. Let's say it's a symmetric matrix because let's say you take the same path both ways. Now the question is, suppose somebody gives you this data, is the distances, and they ask you, give me vectors for Bangalore, Mysore, and Chennai. That is equivalent to asking what are the coordinates of these cities on a map. How would you come up? How would you solve this problem? So first of all, is this a distance metric? This matrix, does it define a distance metric? In this case, it's easy to verify because we only have 3 cities. Let's say we just draw a graph. We don't know what the coordinates are, but let's represent them with a graph. You have Bangalore, Mysore, and Chennai. Okay, and let's say we know that, okay, Bangalore, Mysore is 135, 320, and 400. That's a graph, right? So now, can you think of how would you verify that this is actually a metric? So for that, you need to know what a metric is and so on. So if you're flying in straight lines from between these 3, then this will form a triangle, right, on the map. And if it forms a triangle on the map, then these edge lengths have to satisfy certain triangle relations in the Euclidean plane. If you embed that in the Euclidean. So I've given you the intuition sentence. So more formally, you would say, if you embed this in 2D Euclidean space, then it is only possible if this matrix satisfies certain properties. And one of them is that it needs to actually be a distance metric, without which we can't talk about any of this stuff. And even if it's a distance metric, we are not sure it can even be embedded in a 2D Euclidean space. So if I change these numbers, I could potentially think of adding numbers there so that it's not possible to embed them in 2D Euclidean space. But let's assume that all that is taken care of. It would be interesting to know how to do this. Does any of you know how to do this? Okay, if you don't, that's very good, because that's what you'll be doing in the lab today. At the high level, this is what you want to do, and it turns out to do this, you need to, I won't give you the solution fully now because you need to do it in the lab. You need to compute the eigenvectors and sort of, you need to do an eigen decomposition of this matrix in one solution. So one of the solutions proposed for this is called classical multi-dimensional scale. Okay, and what they do, and I've given you a reference to notes where you will read a little bit about this and so on. It involves some eigenvector computation, and then it takes this as input and gives you not that, which is the graph, right? So this is a graph representation. What it will give you is some sort of coordinates. So it will output XY coordinates of each of these. And it looks like this is exactly what we did in the other problem. We want to take the distance metric that the user has induced. It may not even be a metric. Somehow assume it's a metric that they have induced, and you want to come up with vectors. So once you come up with vectors, you can feed it to this other algorithm, which will compute really fast all of this densely connected inference, and maybe that will give us a very good segmentation. No questions? Okay, what this allows us then is to generalize this distance metric. So they were doing everything in the Euclidean space, but by virtue of choosing a different distance metric, we can extend their method to a generalized thing, and we show that it's very useful for interactive segmentation. So roughly it looks like this, right? You take your images, you take your image, you take your scribbles, and then you sort of compute or convert your scribbles into some dissimilarity. So for example, you could say use any distance metric. So you could say use RGB or something, and then it will combine these two to come up with the distances. And then we do this embedding. So in every pixel in this embedding is a pixel. Every point in this embedding is a pixel in the input. So just like we did the embedding of the 3 cities in 2D, here we are embedding every single pixel after it's been affected by the scribbles in 3D. Okay. And then once you do that, you can simply call this as the black box, which is what we did, and we get this. Okay, so you can go through these details in your lab, but essentially what we're doing is what I drew there, right? We take the dissimilarity matrix, we take some point there, and we identify what the coordinates of the point are. And then for each pair, you can find the distance for all the pairs. The problem is this distance matrix is going to be huge. Right? So if you have 1 megapixel, that's how many elements you have, because you have 1 million cross 1 million times 1 million here. So this is a huge matrix. Okay, so storing it is hard. And if you scale it even more, then even other operations, even computation may become really important. Okay, so the whole point is this is the space in which we sample. So what this teaches you is, I mean, forget about the application specific details. I think what you should take away from this is you saw an image, you saw a problem, segmentation, you saw maybe a tool that you could use that the computer vision community has already come up with. And then you saw what the problem with that tool was that it restricted the distance, the space where you could apply this. And then you thought, well, I don't want this space, how can I bring a different space into this space? And you saw a method for that. So all of this stuff you've observed, but you don't know how to go from one point to one point because you have too much computation. And that's the point where this sampling is actually helping. And I think so while doing this paper, I think we worked on for some 3 years, right? And so this was when I was a postdoc, so I was first author and I had to do a lot of the stuff. And what we tried was all kinds of spaces, right? We tried to sample in the space of pixels, we tried to sample in that Gaussian space, we tried to sample all of this stuff. And none of that was really providing benefit. Either the error was so high that it was not useful, or the computation time was not really that different. But finally, when we sampled in this space, it turned out to be amazing. And I'll tell you how amazing that was, right? Shortly. So the complexity, what we did was instead of using this n cross n times n, we used only C samples. Okay, so let's say you take C samples here stochastically, and if the dimensionality of the embedding was P. So once we take the distance metric, once we add this distance to Chennai, Bangalore, we can embed it in any dimension, right? In that case, P equals 2 gave us a good solution, but in some cases, you may have to go to a very high dimensional space to realize the embedding. And there are ways to know what the error is, whether it is at all embeddable and all that stuff. So let's forget about all that. But what happened when we chose C stochastic samples was that we went to a complexity of n times C plus P squared. Okay, which means if your embedding is possible in P equals 5 or 3, in our case, many of our embeddings are just 3, then that becomes a constant. And then there's a C cubed here, sorry, something, right? And in practice, C we took as P plus 1. And it seemed to be sufficient. We took 2P just to be sure for the general thing, and there's some reasons why you do these things. But C turns out to be a constant once you know P is a constant. Okay, so this is still a cost, but it's not very high. The C is very low, it's like maybe 10, 20 max. And so the complexity of this, the time taken to compute this is very fast. So we could do a 1 megapixel image in, I think at the time, in 2 or 3 seconds. And then, so one of the authors in this paper works at Adobe Research. So they implemented it in Photoshop or one of their applications. And they have these ninja coders there who will take academic results and they just, open them, tear them apart, do all kinds of things. And the next time I saw him, he had it running in like fraction of a second, right? So he had millisecond response to do stuff that I was taking 4 seconds. There's orders of magnitude. Yeah, so what I'm trying to say is no, ninja is like very good coders. No, I didn't mean like he's a real ninja coder. It's just it's a term. When you say somebody is a ninja driver, it means they're so good at it. So he's a ninja coder. Yeah, so anyway, that was the conference presentation. But yeah, as you can see, how come there are no results here? It's a bit strange. I remember why. Can anyone guess why? Okay, so I was trying to be a bit cheeky there. So basically, in any conference, the only reason people attend talks is to see what the results are like, right? So when I said thank you here, everyone was a bit shocked. They're like, wait, where's the part that we have been waiting for? So I intentionally did that at the conference. And I forgot now that I did it there. Anyway, so yeah, what about the results? So this is what we did. We took this input, we performed the scribble, and then we said, look, we tried different distance sort of different ways to embed it, and then applied their method and so on. And as you can see, there are scribbles on the grass, right? And it sort of, depending on what distance you use to embed it, to modify the embedding, it changes what results you get. Okay, so if you didn't use any of this stuff, then you get all these speckles. Even if you use the embedding, but if you didn't use, for example, so one thing you always have to ask, I guess, as a scientist is if you combined A, B, C, D, E, and you have a working solution, the first thing to ask is, do I need all of these? Maybe I can remove A and it still works, or remove B or C. So what we had to do was remove different things and show that actually you needed all of this. So here we removed the dense CRF, and it didn't really work because pixels here did not know about pixels here. For example, this pixel would not have been blue if it knew that all these pixels are red and there was no scribble in that area. Okay, so we did lots of errors, measurements where we dilated this, added random spurious. Intentionally, we added wrong training samples. And I think this is something, if you're planning to do machine learning, I would encourage you to do. Very few people do this. And I think it's important, is once you know that you've got a training set correct, working well, actually it's useful to know if you perturb that training set, do you still keep it pretty well, right? So we took this training set and we said, okay, now we're going to choose this yellow region and intentionally, randomly mutate, add wrong training points. Pretend that a user created a lot of errors, and we increased the number of errors on this scale. So at 100% error, that means they marked only half the pixels correctly. Okay? And then we asked, okay, so if you can, let's not worry about this metric, but basically high is telling you that you've done well. Okay? And we saw what happens for different distance metrics that we manipulated. We saw what happens as you increase the number of wrong training samples. Now, if this curve had simply dropped off like this, like our integration curve, that would tell you that perhaps this is not going to be robust. As soon as the user goes outside the actual foreground, you might start getting very, very low. Okay. And we can see that depending on the image, it may not be easy. So we took different images. An image where color was the dominant discriminator, for example, green and blue. And an image where texture is so in this case, texture is the discriminator. And it turns out that which metric you manipulate depends on what the discriminating value. So it doesn't answer the question which metric to begin with. But what it says is, look, you need to be a bit more careful in which metric you choose to start with before you apply all this. Okay, any questions? Okay, so and then we show different results, and as you can see, some of these, like with the ladder and with, with hand-drawn animations and so on, are very hard to segment manually. But we were able to get, in most of these cases, very better than state-of-the-art and very close to reasonable things. And we did quantitative comparisons, and we looked at what happens for different methods that were available. So the second part of the thing is not relevant for the course itself, but I think it's useful to understand how to evaluate your research. So if you came up with a way to solve some problem, it is not done there, right? That is where the work begins. A lot of the work then begins on how do you validate this and how do you present it to the community. So I think that's the part, that's why I think it's worth talking about. And actually, I was a postdoc at that time, and I did not realize the importance because I'd already worked on this for 3 years. I just wanted it out, right? And the paper was accepted, and one of my co-authors were very, very adamant about this. They said, no, these evaluations have to be in there, right? And so we added all of this stuff, and I'm quite happy that we did. Because I think it taught me at the time as well that these sort of evaluations are useful. And yeah, so it doesn't always work, but so it doesn't always work really well, but on average, it did pretty well. And again, just for the reasons that the computer vision people didn't want user interaction, it's very hard to make a blanket quantitative statement. So we could only run a few tests and so on, and hope that somebody would pick it up. So subsequently, I had a master's student implement this on an iPad or something, and it turned out that it actually works reasonably well. That it's an easy algorithm to implement, and you can take. So the advantage is if you've taken a picture on your phone, you can simply scribble and remove all the background. Or if you want to take a picture from the internet and put it on your slides, this is what I found it most useful for. Often you want to remove all this background stuff. You just want to show this, and you can't be bothered segmenting it. So for that type of task, it was reasonably useful. Unfortunately, I did not maintain the code, and when the new version of stuff, all the other libraries came, I don't think my code compiles and runs. It's available on the website. So on my website, if you want to download the code and so on. Yeah, okay. So that's a lot about this. And I think, so this multidimensional scaling idea, we took some samples, right? I said, I was very general about it, because in the lab today, what you're going to do is take some distance matrix and then try to embed it and visualize where the points. Okay. And to make it more complicated, what I suggested as the second half of the exercise is you take the distance matrix, get your points, and then calculate geodesics. So, for example, if you have 5 cities, going from A to E, it may be unclear whether to go through B or C. So you calculate point-to-point distances from this matrix. You have point-to-point distances, and then in your geodesic calculation, you calculate these route traversals. Okay? So you're going to see how to go from A to E. Do you go through B, C, whatever, and you calculate these. You can use libraries online, just any shortest paths algorithm. You get a different distance matrix, right? And then you see if you can manipulate that distance matrix and to get this embedding. After you do that, then you will scale this matrix. So you generate a random matrix, somehow make sure you get a distance matrix of 10,000 by 10,000 and try to embed them and see if you can see the 10,000 points. So I would suggest start with 100 by 100, sample maybe 20 of them and visualize them. Okay. So for this project, actually, we didn't even need to get to the interesting question, where to put these samples. We just used random sampling and it worked really well. And so this classical MDS has been adapted to do this, and it's called landmark MDS, which is that algorithm in the middle, which I showed you now. So what you'll be doing essentially is implementing landmark MDS in the second half, but with some geodesic distances. Okay, so that is for the lab. Actually, there's a bunch of stuff that I wanted to touch on. Yeah, so maybe we should go back to this one here. And there were 2 things. So one, I wanted to talk about this graphics vision. So let's see, what's the best way to do this? Okay, so we've seen that in computer vision, what we want to do is you have some scene. So you have some scene there. So let's pretend that's the interior of a house. Okay. And let's say you have a camera here capturing CCD. Okay. And an image from there may look. So that's the image, photograph. Take it. Okay. The goal of computer vision is to understand this image. So what they try to do in computer vision is to look at this image and make any inferences about the scene. So perhaps you want to know depth. So you may want to know what is the 3D structure of that table. Okay. You may want to know what is the material on that seat. You may want to know what is the size of the room. You may want to know if there was a light hanging here. You may want to know the light properties. Is it bright? Is it daylight? Is it a window? And so on. And then you may want to do a lot of things. Okay, in computer graphics, these are all given. So for this, basically there's 2 things, right? In computer graphics, all this stuff is given. In vision, we want to infer all this. Okay. So in computer graphics, we saw you're given the lights, you're given the materials, you're given the 3D geometry, you're given everything. You're given the position of the camera, you're given the camera parameters, everything. And you want to estimate what this image looks like. And you want to be very accurate so that if you generate this accurate image, then people will be fooled. They think this environment exists, but it actually doesn't. In computer vision, you want to ask, what are the parameters? And as you can see, these two problems have something in common, and traditionally this has been called sort of the inverse problems. So computer vision is the inverse problem, and this is the forward problem. This goes from model to result. This goes to result. So we are asking what are the parameters. Under some model, right? We have some model, which is this light transport model. It has parameters like materials, lights, and so on. In computer graphics, we take the model, we know what the parameters are, and we want to find out what is the result. Computer vision, you know the result, someone's taken a picture already, and you want to estimate the parameters. That's the big difference. As you can see, once you have machine learning, people said, look, 20 years ago, people couldn't do this. CG community couldn't generate reasonably good images. Now we can very fast. And what we are interested in is not solved. But we need a lot of training, so we are using these people to mark all these things. So what the vision community said is, why don't we use the forward problem solution to train the inverse problem? Because here we know the parameters. So if we generate 1 million images with known parameters, and feed them to some network, deep network, to learn something about it, can we then use that to give a new result, use the learned information to arrive at the parameters of the model. Okay? And this is called inverse graphics. Some people call it inverse graphics. So, people will tell you graphics is the forward problem. They will tell you vision is the inverse problem, and then they'll say they're working on inverse graphics. And you'll say, why not just call it computer vision? You can, but it's because when you say computer vision, people are thinking of all the stuff that I said in the first page. Whereas currently, when people say inverse graphics, everybody understands, oh, you're working on this learning problem. So the minute someone says inverse graphics, you should realize they're talking about learning, training, using computer graphics, and probably have some massive, deep network somewhere, training, and so on. Right? That is, there are people who do inverse graphics without networks, there are CNNs as well, but most of them try to use them. So that's this space. Okay. Did you have anything to add with this? Yeah. Yeah. So you mean with respect to vision or with respect to graphics? Okay. So with respect to graphics, I think the mesh community. So that somebody sent me links. You sent me links, right? And one more person, I think, did you send me a link? You sent me the references. Did anyone else send? No, I got only 2 emails. Did you send me something? You sent me some, Neha. Yeah. What was yours? Curve reconstruction. Did you send me a PDF? Can you send me a PDF? Then tomorrow we will discuss some of those things. Okay. So yeah, I will discuss your stuff as well tomorrow with that because I need to read it properly. Okay. Yeah. So tomorrow we will talk about those mesh things, but briefly. So again, mesh processing had some kind of history. So for others, when they say mesh, they're basically saying if you have a shape, so let's say a sphere, it's easy to represent, right? You can simply choose the center of the sphere and the radius. You have defined the sphere. So it's a very simple representation to have the center and the radius. And it's a parametric representation where you have 2 parameters that define exactly what the sphere is. And now you can answer all sorts of queries like, is this point on the sphere? Is this point in the sphere? And so on. However, for more complicated objects, like we see every day, for example, those curtains, you can see the curtain sort of bent there, deformed. things like that. It's very hard and many times impossible to come up with these sort of parametric representations globally. Okay? So in practice, what people do is instead of storing this as a sphere, they may choose to sample it, put some points on it, and then connect the points with edges. So obviously, if you only have a few points, you will end up with some mesh like that. And sometimes you may not even identify that this is actually a sphere. But topologically, because of the way you sampled and connected it, you can make sure that it is like a sphere. However, in graphics, this is what people use. And to make things simple, they impose certain constraints on these meshes. So that's your mesh representation. And you can say that meshes, you can say, let's only focus on triangle meshes. Okay? There you're saying that every face here needs to be a triangle. And so on. You can have a mesh with only quadrilaterals. So obviously when we designed these things originally in CG, there were artists who would go in and draw meshes in 3D or sculpt them. And it was easy to obtain these representations. But now we want to get these meshes from real objects that exist. Okay, we may want to get them from by using a scanner. We may want to get them with stereo images. We want maybe a Kinect, a Microsoft Kinect, or any other different acquisition device. And what happens when you do these acquisitions is just like we had with images. Now we get raster scans of them. So most scanners, sort of either image-based, laser-based, or even sonar-based, what they end up doing is instead of the sphere, it spits out like this, points. Right? The difference between these points and the points that the artist generated is that the scanner doesn't tell you how to connect these points. Scanner just tells you there's a 3D point there. It doesn't tell you which point is connected to it. So the mesh community for a long time has worked on this problem of meshing. And they worked on something called remeshing. If you remove some of the vertices for example, you may want to remesh. They worked on something called what is that word? Mesh simplification, which tells you how to simplify this mesh. So if I want to remove vertices here, which vertices should I remove so that it still looks like a sphere or it has some low error to the sphere? So there's different error metrics. So people would probably look at L2 distance, Hausdorff distance between, and any other metrics that you use? No, basically it's these two. Okay, yeah. So you can use these metrics to tell you how far away from the sphere this sample sphere is. Okay? And this simplification can be measured based on this distance. So if you simplify the mesh and somehow are able to compute the distance to the original mesh, it's like your integration error. As you remove samples, as you increase the sampling, you want the error to drop, right? Yeah. Yeah. No, it has nothing to do with just the geometry. We don't know how to store the geometry or the shape of, let's say, something like this, or the water bottle. How will you store it? When you scan it, it will tell you there is a point here in XYZ. It will tell you the XYZ coordinates of all of these points. So let's say I fix this here, and I scan it like this. It will tell me this point here is XYZ. This is X2, Y2, Z2, and so on. So the output of the scanner is a number of XYZ locations. So you will get back that, okay? Yeah. Then what you want is to be able to do things on this mesh. So you may want, for example, to determine if a point is on this mesh. So just like you did with the sphere, right? Let's say you want to know whether this point is on that mesh. How would you know? Not for the sphere, for this mesh. For the scanner that is giving you this mesh, let's say that's a simple operation I can think of because I mentioned it there. Somebody gives you an XYZ location and asks, is this location on the mesh? How would you do it, right? That's what the mesh community started with. Like, we need to answer simple questions. Now, for this, if this was all triangulated, then we know this is planar. Then we can take these 4 vertices and check for every set of 4 if the point that the query came in with is on that plane. If it is, then you say, for this given approximation, we say it is on the mesh, right? And the problem is, if your approximation is very coarse, then you will give the wrong answer. You will say it's on the mesh when it's actually not on the sphere, it's just on that plane, right? From the scanner, yeah. You just create the mesh. And then there's meshing algorithms that I wrote there are ways in which you create the triangles or the quadrilaterals. So meshing tells you how to take the points and create polygons. And remeshing tells you, if I remove a vertex, how do you recreate the polygon? So obviously it's non-trivial, right? If you have a triangle mesh, so if I have, let's say in just 2D, if I have this, and I remove this vertex, that point, what are you going to do with the triangles? You obviously need to remesh it, right? So you're going to keep those triangles, and you know these edges exist, so maybe you will create totally new edges there. That's called remeshing. Simplification is a way of telling you which vertices you should remove. So yeah, that's what I'm coming to, right? What is the use of sampling in your integration? Right? Ideally, everyone should use infinite samples. It is not computationally tractable. So at some point, you want to reduce the number of samples so that it's useful. Similarly, if you scan an object with something, you will get millions of points. And at that point, you say, okay, look, we can't work with this. We need to remove points. Okay, you can randomly remove points, but that's going to be hopeless. So it's going to give you very high error. So then people in the simplification community said, take a metric and choose methods that once you drop these points, result in lower error, right? According to whatever metric you want. So that will tell you which points you can remove safely. Okay. Now the problem is these errors may not be focusing on what is perceptually important to us, right? So for example, if you have a unicorn or a rhinoceros, right, and I remove one vertex there, that feature, let's say, disappears. In terms of L2 error or Hausdorff error, because let's say the rhino was really big, let's pretend that's a rhino, okay, was really big, the actual change in the error quantity is very similar to what we talked about for images. The error itself, in terms of a numerical quantity, is not that big. However, once you remove the horn of a rhino, its distinctive feature for us perceptually goes away, right? So then the mesh simplification community said, okay, this may be insufficient, right? So they said we need to account for what are called features. So they said we need to preserve features. So they said, okay, we need this concept called feature preserving simplification. And this is obviously ongoing research. I mean, nobody really knows what a feature is or anything. And the mesh community was working on a lot of these, and there are many other problems that they work. So for example, mesh editing, right? This is like you take that mesh and then you do some changes. Then you want mesh quality. For example, maybe I'm not even going to use this in an animation. Maybe that's the mesh of an aircraft wing, and I need to push it through a simulation, so a finite element method or something. And maybe the quality of the mesh for that finite element method is not good enough. And your L2 error and everything may tell you it's exactly the same wing, but when you run FEM, you get very high errors. So you need to improve the quality of, so there's analysis involved in all of this. Okay? So these are all problems that the mesh community has been working on for many, many years. I would say this is probably, so obviously these are the first things we did. And I'd say of all these, feature preserving is probably the most recent. But even that, I would say, is probably at least 8 to 10 years old, right? 10 years? Is that the, yeah, okay. Yeah, of course. Everything people are still working on. But I would say when it appeared was 2008 something. Okay, so almost 15, 18 years. Okay, so that's the thing about preserving, right? Feature preserving. And then what happened was people said image editing. I want to take a mesh. I have another mesh, so I've scanned. Now I want to somehow combine these two meshes. And this is useful for a variety of reasons. A, that many scanners cannot scan the whole object. So you may get, so for example, in the sonar example I showed you, on the first day, the vehicle may measure this part of this thing today. Tomorrow it does another patch. Every day it's scanning. And then in the end you want to put them all together. So then you want to edit these meshes by combining them, merging them, and then you need to register them, and all these kinds of technical terms for mesh editing. And people have been working on those as well. And again, here you have two communities. One that say that human interaction is useful, where a human will suddenly point out features and say, I think these two are the same. So you have correspondences, what we saw in image. You have these on meshes, which point corresponds to which. And then there is the same segmentation. You give a mesh. So all the stuff that we talked about for images also applies to meshes. You're given the mesh of a horse, and they want to segment it into the legs of the horse. This is all very relevant for machine learning, because when you want to give it labeled data, you want to give it horse, legs of the horse, and so on, if you want fine-grained classification. But humans at that grain would take a lot of time, so perhaps you can use some of this information, right? So, for example, you could take a horse model, render it with CG, and use a mesh decomposition or segmentation method to know where the legs are. Then the CG image will know where the legs are. You can label every pixel as leg of the horse, and then train your inverse graphics algorithm. Right? So you can see how all of this stuff just comes in to play for one application. Okay, and it all seems like they're all totally different communities, but actually in modern research, they all kind of come into play. So you can't really simply cut out one or the other from the scope. Okay, so that is a lot of the stuff mesh people used to do. I think the recent trend in meshes is, I would say, what is it? Yeah. So, what is the word? Oh, actually, I wanted to talk about this. So they try to identify alternative spaces, right? Which means, let's imagine that there is a manifold, some surface, and this point here represents an aircraft. Now I've taken an entire mesh and I've computed a feature vector which is like 1 point, right? So that has a vector we've seen just before. So this is a vector v1, and this is the plane p1. I have another airplane, okay, some stealth plane, and this may be a vector v2, that's v2, okay? Now this space would be useful because then as I walk along the space from P1 to V1 or V1 to V2, I can, at every point, if I can generate, so let's assume this is the mapping M. If at this point I can generate M inverse like you did with the CDF, then you will get some plane, which is some hybrid plane. So imagine you could simply go from here to here smoothly by linearly interpolating in this space, or a geodesic, or whatever you want. And then for every point in that curve, if you can generate another plane. Now this would be of a lot of interest for people who are modeling, right? It is all, yeah. So previously, people looked at it as a parameter space. People looked at it as there are some parameters, you vary the parameters, and there is some mapping here, and you can look at it as maybe a regression problem or something like that. The modern trend, of course, is to use CNNs. So the current approach is to look at it as a latent variable space. Okay, you can read up about this. I'll just leave that term there so you can read it up. So essentially what you're saying is there are a lot of things happening. We talked about survey sampling where you may sample people and find out about, who has modes of transport, which part of the population is happy and all that, right? So that's what you sample. That's the data you observe. N people said they were happy. N2 people said they have enough food for 3. And N3 people had income above 500,000. Very measurable, observable variables. But the underlying causes for why N people could not eat for 2 days is not something you get from the data. So a lot of that analysis requires you to look at variables that you don't measure but are inherently causing some of the measurements to be what they are. And those are called latent variables. And there's different ways in which you can extract latent variables. And people did them with different tools. So I showed you those curves, those peaks in the computer vision community. Every time there was a peak, somebody tried to use that tool to look at latent variables. Yeah, in the previous version, so people looked at Gaussian process latent variables. So they are called, for example, GPLVMs. Okay, now obviously because there's all this convoluted neural nets, there's deep nets, what people do is they use what are called autoencoders. So for example, you can look up variational autoencoder. Okay. And the way it works is, maybe you don't have details to get into all that, but time to get into all that detail. But the way it works is you take your input and you keep reducing it down in dimensionality. You take whatever is this lower dimensional representation, you keep inflating it till you get back this same dimensionality by randomly doing stuff. And then you take training data, give it here, see what you get back. And then take the distance between these two, feed it back, and keep repeating till the weights you learn give you the minimum distance between the two high dimensions. And once you've learned that and the distance is low, you can chop off this generative part and you end up with the low dimensional, the mapping to the low dimensional space. And this is the general idea of autoencoders. So you can look up variational autoencoder, which is why I put it there. This space has now become very interesting because people are using it for all kinds of applications. People are doing inference in this space. People are using it to generate models. People are using it to generate. It is not genetic in that there is no mutations. Okay, it is not. Oh, you mean this LVMs, latent variable? This one, this space. It is not really genetic because. Yeah, so you can, yeah, exactly. So you can have this idea of the space for everything. Pretty much everything you can look at, yeah, you can look at DNA, you can find this latent space and see. So anything, any measurable thing. But since we're talking about meshes, I said this is a very active trend in the mesh community. I would say over the last maybe 5 years or so, people are using this to do a lot of interesting things. There was one more I wanted to say, yeah, so. And the last thing I would like to say about meshes is obviously a lot of the deep net stuff is geared towards images, right? Computer vision people have developed them, improved them, adopted them. So they require your data to be in a certain form. For example, the image grid form. Meshes or points are not conforming to this. So it was unclear whether you could even use all that framework for this. People have been using it, but there was no systematic work. So recently, I think at SIGGRAPH this year, there is some work on CNNs for point cloud. I don't remember the title, but it does something like this. So you can see SIGGRAPH 2008. Okay, there is this. So I would say in meshes, there is still a lot of interest in all of this stuff that I talked about. But as far as I can understand, these are the modern problems that maybe if you did your PhD and took courses 3 years ago, 5 years ago, you may not even have seen, right? Because it's very new stuff. And as far as I know, all the guys I know on meshes are either like working on hardcore sampling and analysis and stuff like Mark Pauly and all these guys, or are doing this like Niloy Mitra and all these guys, right? So one of the problems of using certain tools is that they cannot impose certain constraints. So when they were using some other older tools, they knew how to impose certain constraints. So while we're talking on this, no one's told me lunch is here, so I'll assume it's not here. Let's see. So while we're talking about this, I'll show you one of our recent papers. So what we did here was, instead of walking the manifold of meshes, we walked on the manifold of materials. So for example, that is a material, right, which is somewhat diffuse. This is a material which is very shiny. And this is material which is very diffuse, has some other property. What we said was, if you have a space of materials, that is what you see here, every dot, you don't need to read anything, just everything that has a label attached, this is the space of materials, and these are all the labels in the space of materials. And that dragon there tells you what each material looks like. So here's a scene. You can see the coffee table has some, kettle has some, and as this mouse pointer moves in this space, the material of the teapot is changing. Right? Now, obviously, there are two challenging parts here. One is you need to be able to interpolate. So as soon as you go anywhere between, you need to know what the corresponding material is. You need to compute that. But the more challenging part is, once you know that material, how do you render the scene? You have to do the whole light transport. So what this paper's goal was to be able to walk this manifold without having to recompute the integral. So we said, if you pre-compute the integrals at these known locations, then we said, using our method, as you walk the manifold, you can also recompute the integral. Everything is fixed. Only thing that is changed is the material. So the key contribution here was, not only are you walking the manifold and knowing what the material is, for that material, you're also recomputing the entire integral instantaneously, right, within like 50 milliseconds. And remember, this has multiple reflections. It has complicated, you see the lights there. There are multiple windows, so the number of photons, all the transport you have to do is very, very high. Reflection. Yeah, that's what I'm saying. So all those integrals have to be computed really fast. So sometimes it is not just about finding the latent space, right? You can always find some latent space. The question when you do these kind of analysis or approaches is to ask, why is this latent space useful? Because if you come up with a latent space that's not useful, then it's arguable whether it's interesting, right? Sometimes you can come up with an interesting latent space without knowing what it's useful for, but that would not be publishable in a graphics. Or so perhaps at NIPS you can imagine publishing just, here's an interesting latent space. I don't really know what it's useful for, but so it depends on what your target is. So in graphics conferences, obviously they're not just happy with you coming up with the latent space. They want to know why is it useful. So again, here we showed, as you move between all these materials. So these materials have been acquired by somebody. It's a public database, publicly available database. And remember, each measured material is 4 dimensions, because for each material, there's an incident ray, there's an outgoing ray, and there's a probability density associated with every pair of incident and outgoing. So it's 2D, 2D, 2 cross to 4D, for every 4D, you have a probability density. That's what you measure. If you're doing colored materials, then it's 3 probability densities, one for red, one for green, one for blue. So you have a 4D surface that has been acquired, and this data, every point here is one such 4D. Remember, because it is acquired, the same problem with meshes, this 4D is highly sampled. So we actually have 1 million samples per 4D measurement. So that point there is 1 million measurements. Okay? We're moving from one set of 1 million measurements to another set of 1 million measurements while keeping it still as a plausible material and recomputing integrals even when, in this extreme case, the geometry is changing, the lighting is changing, and so on. So the difference between this and the coffee table is here we're not accounting for multiple bounces. In the coffee table, we were able to account for multiple bounces, but we don't expect anything except the material to change. Here we can change anything, but we can only do one bounce, sort of a trade-off. And that's the whole space of materials. So I think this started to be a common trend, not just in meshes, but in many parts of graphics about 7 or 8 years ago. And so we started this project when was this published? Oh, this was published this year, but we were sort of doing this for a while. And so Cyril is also, he's a senior faculty in India. And so somehow we didn't have a student who worked on this, so we were coding everything, and it took a very long time to actually ship it. But actually, we'd been discussing this when it became a popular trend. This latent space. Well, in this case, the manifold is 2D. So this is a 2D. No. Yeah. Yeah. So how did we do this? I don't know if there is a. Yeah, it's a good question. No, we have not thought about it. So in this case, how did we do it? So in this case, because we used GPLVM, I think it's parametric. So then it shows the parameters. But otherwise, yeah, I think it's a problem. It's semi-parametric. How things are varying when you move from one. Yeah. So that's what this is, right? So this is one material, this is one. So, but here the pointer, there's a pointer. Yeah. So this color coding we used the albedo. So we said the average integrated material property. Something we had to give. Yeah. So yeah, we didn't think carefully about it. We just wanted to show some map. What people commonly do is this color map. They provide uncertainty. So this particular latent variable mapping tool, which is Gaussian process latent variable mapping, gives you also uncertainty. So it gives you the manifold and the uncertainty. So basically, if you ask it here, it will say, I'm very uncertain because you're far from all the data points. So usually when people visualize this, they show green and red, where green areas mean we're fairly confident, and red areas mean. So a very visual place you can see this is one of my friends did this paper on font manifolds, turning a manifold of fonts. Right? And in this particular paper, if you've not seen it, you can see this latent space traversal very visually. That's slow, really. Because it's just an HTML page. It's up to you. So actually what we did in some of them is we had a 5-dimensional latent space and we only displayed the first 2. But in many we also had a 5. So yeah, so maybe that's why it was slow. So Neil is not at UCL anymore. He now has a position. Let's see if there's a demo or something. Yeah. So what you see here is the same space, but for fonts. So instead of training it with materials, this guy, he trained it with fonts. So you can see in their case, they showed how unlikely you are to find a good font. Okay. So now if I move this point around, you see the font changes. And all these dots here are fixed fonts. So this is one font and this is another font. And you can see that as you go between them, the font changes very slightly. So you can customize your font potentially to a value or to a style that no one else in the world might have. And now people have actually done some very interesting work. They've, based on this, there is a recent work, I think from Korea, where they send you a letter, you scan the letter with an app, and there's a secret code. How is there a secret code? Every single alphabet in that letter, it will try to find out which font is being used. And because if you move around very slightly, you don't even see that the fonts are different. But their algorithm will detect it, find out from here, inverse, map this to the locations here, and the code is in this space. So you'll get a letter saying, thank you very much, but then the code will say, sorry, we can't meet, or something like that, right? And it's a very interesting application, actually, because it's really hard to crack this, unless you know all of this stuff, right? And they have control over what the dimensionality and so on. It was a cute demo, actually, at Signal, where they showed this stuff. So so what I'm saying is, when they came up with the manifold, these guys didn't really say what it's useful for. It just looked like a nice way to display fonts. And actually the fonts look reasonably good. So now if you go into areas where you don't know what will happen, actually you still get fonts. You just don't know, you can't provide any sort of guarantee that it will look good. Right? Whereas these have been designed by specialists. So if you stay in that red zone, you're pretty decent. So now you can apply this to almost any field, right? I mean, you can, any sort of data. Yeah. And so not just fonts. I'm saying you may be doing anything. You could do meshes. You could be doing medical sort of tumor contours. You could map it to whatever you think is useful. And its main power comes when you have some very high dimensional space. In this case, the font has all these vertices here, right? So if you have to specify all these things, you'll have a very high dimensional vector. And then it's parameterized based on which letter and so on. So your space is very high. In our case, it was 1024 by 1024 measurements, so 1 million samples. And in that case, it's very beautiful to see that at the end, it only depends pretty much on maybe a handful of variables, 2 to 5 to 10. Yeah, so if you think about the simplest way to do this, you can take that high dimensional space and do a PCA. Simply do a linear thing and chop off and take your most important subspace. Right? So your PCA may give you a very long list of eigenvalues. And you can say, I will only take the most, say, significant 3 eigenvalues and remove everything else. And you will still get a mapping. The problem is when you start having things that are nonlinear, PCA doesn't help, right? Because it's a linear reduction dimensionality. So this is actually a dimensionality, can be seen as a dimensionality reduction tool. And there are many, many dimensionality reduction tools. But it works really well in the nonlinear case where the data actually does have some latent variables, right? And they are not parametric. So a lot of the classic dimensionality reduction, they are hoping there's some parametric connection. So for example, you have the Swiss roll data, things people have been looking at for many years. You know there is a spiral, you know there's a plane that has been rolled or something. Or you guess there is some parametric thing. Whereas in this case, you know there probably isn't a parametric representation, but there is still some space where there is a reasonable sort of connection between all of these data. So I think that now the more recent version of this, I think you have to look at variational autoencoder images. Bharat, lunch ready aita? If he's watching, he should hear me. Okay. So yeah, so here's a 2016 paper from your alma mater, I guess. Right, so you know them? Okay. So let me see, just jump to the example. So is that NIPS? NIPS means they may not have proper images. You'll just have a few plots. Yeah, you only have this. Okay, let's see what it says. Okay, this is captioning. We looked at this, right? let's look at generated caption from unseen images. So they were given this image, they'd never seen it before, and the caption says, a man with a snowboard next to a man with glasses. Okay. And says, a player is holding a hockey stick, big black dog standing on the grass, a desk with a keyboard. A man is standing next to a brown horse, a box full of oranges. A box full of apples and oranges. Clearly it got it wrong there, right? Yeah, so this is not very useful because they don't actually visually show yeah, so this is very similar to the font thing, except instead of using Gaussian process related variable model, they use a variation model. So here, I think the lesson is the underlying idea of having a latent space and traversing it should be decoupled from how you achieve it. Okay, there are several tools. There are many tools to achieve this latent variable optimization. Depending on your data and application, one may be better than the other. I think a lot of people now, especially students, assume that this means latent variables and that's it, they're equal. But they're not, it's just one tool. Yeah. People use it for that. Actually, there's in the UK, there is a community called Digital Cultural Heritage, where they use it to complete. Actually, we had a paper. I'll just show you the result. But here you see, none of these digits were written by a human. Okay, they were all, what they did was they took digits written by a human, they formed this latent space, and now they traverse the latent space to generate all these numbers. And so the algorithm only knows a grid of 64 by 64 pixels. It has no information about what a number means. It just knows white and gray values on a 64 by 64 grid. Yet it is able to restrict its generative model only to some things that look. Now, why is this useful? This is useful because when you want to do recognition of script or things, you can be robust. If you project it to that space, you can be robust because there's a pretty large area there where you can generate similar looking digits. So this is fairly an active area. People don't fully understand some of the things about this. And I think even this year, 2018, there was a pretty breakthrough paper on this topic. Yeah, so you can use it for completion. I mean, we had a paper. So this paper is with Neil, the guy who did the font manifold. He had this paper on completion. So here we took some scripts. So here there's a Chinese script. And so we took a database of scripts and pretended that there was a problem by removing, kanji. So we removed parts of the script and asked the algorithm to compute it. Okay, in this case, you see for a horse, we removed different parts of the horse and asked the algorithm to complete it, and it was able to complete it like that. Obviously, it doesn't need to classify this as a horse to do this. And I think this is one of the trends that you see now. I think a few years ago, people would be looking to understand it's a horse and then use that information. And then they realized that is overkill. For many of these things, in this case, we had no idea what a horse is. We created this manifold and then we said, oh, if we complete it like this, and then walked around on the manifold till some error was reduced and said, oh, that must be reasonable. Right? And it generates. And obviously, there are places where it fails. I don't know if this shows one of them. But there are many places where it fails. It may show you things that are not on. Okay, I think let's end there. We've been going for quite a while.